All right, guys, good morning. Today what we're going to be doing is walking through investigation number 12, where investigation number 12 is a hand warmer design challenge. Okay. What we're given initially is some specific parameters for the design of a hand warmer. So what it states is that the ideal hand warmer increases in temperature by about 20 degrees Celsius, but no more than that. And it does so as quickly as possible in a volume of about 50 milliliters. In addition to that, it's a cost-effective substance, and the substance itself is safe and environmentally friendly. We're going to carry out experiments which allow us to determine, after experimenting with about 6 different substances, which substance and in which amount we can use in order to make a hand warmer that kind of checks all those boxes. Okay? So some background information, stuff that we've already learned. What we understand is that breaking bonds and overcoming intermolecular forces requires energy. So if that's happening, the process itself is absorbing energy from the surroundings. And conversely, what we know is that forming new bonds or forming new attractive forces releases energy. So the process would release energy to the surroundings. When an ionic salt dissolves in water, ionic bonds between the cations and the anions in the ionic solid, and then those hydrogen bonding forces that exist between the water molecules are disrupted. Those particles move around, and now we have new forces of attraction between water molecules and anions and water molecules and cations. The amount of energy required to overcome those forces and the amount of energy that is released when those new forces form will result in an overall energy change for the entire process. Okay. Sometimes these processes are endothermic, and sometimes these processes are net exothermic. What we understand is that sometimes, if it's an endothermic process, so the dissolving of an ionic salt actually results in a decrease in temperature, that process still occurs spontaneously because of a concept called entropy. Entropy is a measure of disorder, and because the dissolving of an ionic solid results in an increase in disorder, that's considered to be favorable in terms of thermodynamics. So in this lab, I'm going to change my view here. We have a practice part, and then we have an application part. In the practice part, what we're going to be doing is dissolving a solid in water. That solid is an anhydrous magnesium sulfate, measuring a temperature change, and really the whole purpose of that is to practice for when we have to do this and we care about our data in the inquiry portion. The other part of the beginning of this lab is to calibrate our calorimeter. When we calibrate our calorimeter, what we're going to be doing is mixing equal volumes of water at different temperatures. What we know regarding the law of conservation of energy is when we mix those 2 volumes of water at different temperatures, heat in the form of thermal energy will spontaneously flow from the hot water to the cold water. It will continue to flow until the 2 samples of water combined reach a final temperature, the same temperature. And according to the law of conservation of energy, the amount of energy that was transferred from the hot water to the cold water is equal and opposite to the amount of energy gained by the cold water from the hot water. That's assuming that we have a perfect little universe in our coffee cup calorimeter here. Unfortunately, it's not perfect. The calorimeter itself will also gain some energy from the hot water. And so what we're going to be doing in the second part of the lab is determining how much energy the calorimeter absorbed from the hot water, and then calculating a heat capacity for our calorimeter, which we can apply to the second part. I know I said second part already, but the second part is truly the inquiry part, and we're going to be taking into account the heat capacity of the calorimeter when we do all of our data measuring, experimenting, and so on and so forth then. So as I said, to start, what I need to do is simply practice what my procedure will be a little bit later on in the lab. And what I'm asked to do here initially is to assemble my calorimeter apparatus, and I have this here. I have a stir plate, my double insulated coffee cup calorimeter. Within there, I have a stir bar, which you may or may not be able to see. I have my thermometer, and then over here to my right, I have water, and I have two different solids. Okay. First thing I'm asked to do, once my setup is complete, is to measure out 100 milliliters of water. Okay. Gonna look. All right. So the way that my graduated cylinder is calibrated, I can measure to 1 decimal place, so I can say that that is 100.0 milliliters of water. Knowing that the density of water is 1 gram per milliliter, I have 100.0 grams of water. I'm going to add this to my calorimeter, and I'm going to set my calorimeter to stir. I set it to stir because I want it to, I want the heat to be evenly distributed in the water once the experiment gets started. All right. I also want an accurate reading for my initial temperature. So I'm going to turn on my thermometer, and I'm going to do just that. I'm looking to write down an initial temperature of my water. I see that the initial temperature of my water is 20.9 degrees Celsius. So I'm going to record that. Okay. In the meantime, I'm going to turn on my jewelry scale. I'm going to take a weighing boat, press tare, and I'm going to measure out 5 grams of the substance magnesium sulfate. Doesn't have to be perfect. However, I do have to record the mass that I add. Going, keep going. Okay. A little bit over, so 4.52, or I'm sorry, 5.42. I'm gonna keep removing it though. All right. I'm at 4.99 grams, and I'm going to record that value in my data table. And the next step, what I'm going to do is I'm going to add the magnesium sulfate to the water in my calorimeter, and then add my lid. I'm going to be careful to add it all. Try my best, still not all in there. I'm going to add my lid. And what I'm looking to do here is carefully monitor my thermometer and record the highest temperature it reaches. I'm at 24 degrees Celsius. I'm waiting to see if it continues to increase. It's not changing, so I'm going to say that my final temperature for this part is 24 degrees Celsius. As I said, the purpose of this part is simply to practice a procedure that we are going to carry out for 6 different substances in the inquiry portion of this lab. Now, the second part of this lab involves calibrating the calorimeter. So, I'm going to stop my video. I'm going to take a moment. I'm going to clean my materials, and then I will return to carry out the calibration part of the instrumentation practice for this investigation. Okay guys, I'm back for the calibration part. What I've already done is measured out 100 grams or 100 milliliters of cold water. I'm going to add it to my calorimeter. I'm going to set it to stir. And I'm going to measure my initial temperature here. I'm going to give it a minute to equilibrate, and in the meantime, I'm going to add or measure some warm water out in my graduated cylinder. Again, I'm looking for 100 grams or volume of 100 milliliters. Now, they suggest that the temperature of the warm water be about 50 degrees Celsius, but I was a little overzealous here. Let's see what we got. Continuing to go up, so I just need a minute. I have an initial temperature of 59.8 degrees Celsius for my warm water and an initial temperature of 21.1 degrees Celsius for my cool water. And now what I'm going to do is combine the two and allow them to equilibrate in temperature. Oh, I wasn't expecting that. Put my lid back on. And I'm going to watch the temperature change. The temperature is continuing to increase, but it shouldn't take long for it to equilibrate. And what I can see is that I have a final temperature of 39.4 degrees Celsius. In a moment, I'm going to walk you through some calculations that will allow us to use this information in order to determine the heat capacity for the calorimeter. Alrighty guys, I'm here to help you through the calculations for the calibration of your calorimeter. Alright, so in the calibration part, what we're going to be doing is using the data that we collected for the hot and the cold water in order to determine the amount of energy that was absorbed by the calorimeter, and then the heat capacity of the calorimeter. Once we have the heat capacity of the calorimeter, we can apply it to all calorimetry experiments that we conduct in the inquiry part of this lab. So if you look here on the left, what I have is my data. I have my data for hot water here. I have my data for cold water here. Okay? What I need to be able to do is use my equation for Q, which is MC delta T, in order to calculate the energy that was released, that's here, by the hot water, and then eventually the energy that was absorbed, by the cold water. Now, of course, these are just values that are calculated through Excel, and they don't observe significant digits. What I can tell you here is that this is 100.0, and so is this mass, and everybody else is listed correctly in terms of significant digits. All right, so if you can't already tell, it looks like we're going to be limited to 3 significant digits in our answer. So hopefully that's going to help you to be able to round these values. All right, so keep in mind C for water is a constant, 4.184. All right, I'm using that for both of these. Now ideally, energy that was released by the hot should be equal and opposite to the energy that was gained by the cold. However, in this lab, some energy is gained by the calorimeter. All right, so what you can see here clearly is that the energy that was released by the hot and the energy that was absorbed by the cold are clearly not the same. So really what I have here is Q hot plus Q cold plus Q calorimeter, that means the energy that was absorbed by the calorimeter, should add up to 0. If I plug in my values for energy released by the hot and energy absorbed by the cold to here and here, I can subtract and determine the energy that must have been absorbed by the calorimeter. And that value was done in Excel, and it's here. Again, not according to significant digits. I hope you guys know the units for energy by this point in time. In the end, what I know about the calorimeter, the energy that absorbed by the calorimeter has to be equal to its heat capacity, time or specific heat, times its change in temperature. So I have this value, and for delta T, I'm going to use the delta T, so here, same as cold water. So that means that my delta T here, if I'm looking at the cold water that I'm using, is 18.3. When I plug in and I solve, I find that the heat capacity for the calorimeter is about 48 joules of energy per degree Celsius. All right. I think accepted value is probably about 22. Some things to keep in mind as far as error is concerned. When I transfer or when I stop heating my water, that water is continuously losing energy to the cooler surroundings, so it is continuously losing energy. That means that really this initial temperature here of 59.8 degrees is probably a little high. By the time all is said and done and the hot water is transferred to the cold water in the calorimeter, the energy or the temperature of that water has been lowered because energy is continuing to be released to the surroundings. Okay? So hopefully you guys are able to use this information in order to show some work and record your answer for the heat capacity of the calorimeter. For the inquiry portion of this lab, we are going to be measuring data for temperature change as it's dissolved in 50 milliliters of water. We're changing the volume to 50 milliliters of water here simply because that's the volume that is suggested, or that is the criteria that we're requested to meet as far as designing a hand warmer. So what I'm going to do in this part is now measure an initial volume of 50 milliliters of water and an initial temperature for that volume of water. I am then going to measure out 5 grams of each solid, because 5 grams should give me a sufficient temperature change so that my data is considered to be reasonable or reliable. Now I have 6 substances that I'm supposed to be testing. For time's sake, I am only going to show 1, but I will provide data for all 6 once we start to move through and do computation and analysis at the end of this lab. So the solid that I'm going to be working with is sodium carbonate, Na2CO3. So to start, I'll take my graduated cylinder and I'll measure out a volume of 50 milliliters of water. Okay. All right, 50 milliliters of water into my calorimeter. I'll set it to stir. I'm going to give it a moment to equilibrate. While I give it a moment to equilibrate, I'm going to measure out a mass of about 5 grams of my ionic compound, sodium carbonate. Okay. Oh, look at that. 5.00 grams. Okay. My initial temperature here is 23.2 degrees Celsius. I'm going to add my 5 grams. I'll add my lid. I'm watching the temperature increase already. And again, I'll monitor the temperature on the thermometer until it reaches a maximum value. The temperature on my thermometer has stopped changing, and the maximum temperature is 27.4 degrees Celsius. I'm going to take a moment now to clean up my materials, and I will be back with the remainder of the data, and I will help to walk you guys through these post-lab calculations. Alrighty guys, and honestly, I said I would come back and help you with your calculations, but upon review of what's written in the lab document provided by College Board, it's actually pretty clear and well done, which is not usually the case. Hence my coming on to help you guys with calculations. So for these calculations, unfortunately, you are going to be on your own. Best of luck, guys. I'll leave this on for a few more seconds so you can continue to copy down your data.